All right. So, what did we talk about last time? Last time we talked about those sort of standard forms of logic circuits, right? We talked about this kind of terminology we can use, right? A circuit can be an AND-OR circuit, which means it has a level of ANDs and an OR circuit on the output. Or an OR-AND, which means it has a level of ORs and an AND circuit on the output. Or it can be like AND-OR-AND, which means it has a level of AND, a level of OR, and then an AND gate at the output, right? We sort of had this standardized language to define these circuits, kind of in the same way we say sum of products or product of sums to define standard forms for Boolean expressions. Everybody go on that? It's pretty simple, it's pretty straightforward. Now the reason we do that is because of what we're going to talk about today. Today we're going to talk about circuits of NAND and NOR. And there are two reasons that we care about circuits of NAND and NOR, or two things that we're going to do with them at least. The first one is this. Just in the real world, when you're actually building these circuits on silicon, in the real world, NAND and NOR gates tend to be faster and more cost effective than other gates. Right. In the real world, when we're building these circuits, NAND and NOR gates specifically tend to be a lot faster and they tend to be more cost effective, which means they require fewer transistors to build a NAND gate than it is to build an AND gate or an OR gate than other gates. So what that means is, and the purpose of today's lesson is, we will try to convert our logic circuits to circuits consisting just of NAND gates or NOR gates. Our logic circuits to composed of NAND gates and NOR gates. And it turns out it's actually pretty easy to do. We'll try to convert our logic circuits to circuits of NAND gates and NOR gates, which means we'll do the thing that we've been doing, right? We'll get our Boolean expression from our truth table or our generalized min-term or max-term expansion. Oh, another thing. Oh, by the way, what is live right now? It's right? Anyone looked at it yet?
Nope.
Nope. This is important. We noticed this also in assignment number 3 when we were doing the grading. When I say min-term or max-term expansion,
Either or?
what do I mean?
Either or?
What's that?
Either or?
No. The question asks you to give us the min-term expansion or the max-term expansion. What is it asking for?
All of the min-terms for that expression?
No, that's the important thing, right? A lot of people, and this is on me maybe for not communicating as effectively as I should have. A lot of people think that this means the Boolean expression, right? A, B, C, or A, B prime C, and so on. That's not, when we say min-term or max-term expansion, we mean this business. The, sum of min-terms, 0, 1, 3, that one, or the product.
Oh.
Max-terms, 0, 1, and 3, so. Right, so when we're asking you for that, this is what we're asking for.
I think I messed that up a few times.
A lot of people mess it up. Like I said, that's probably on me.
We lose points for them?
I don't know, already did. But I'm bringing it up right now because you have an exam. This is what we're talking about. So when a question that asks for this on the exam, this is what we're asking for. It's a little bit vague.
So what will the wording be if you're asking for like the first?
We'll be asking for the Boolean expression.
Okay.
Yeah.
Boolean expression.
Yeah, so if we're asking give us a, simplified Boolean expression, that's what we're asking for. This is what we want. If we say, give us the midterm expansion, this is what we want. Okay? All right. Cool. All right. Now there is it. So first, let's talk real fast about NAND gates and NOR gates, and specifically, how do we sort of transform a thing to NAND gates and NOR gates. So first off, everyone can probably guess what a NAND gate is. What is it?
Not and.
Yeah, it's not and. It's not and. It's the inverse of and. So what we'll say is, we'll usually draw it as a thing that looks like this. Maybe we got x and y. We'll draw a NAND gate, or excuse me, an AND gate, with a little dot on the end to indicate that it's inverted. And that's our output. We'll say that f is equal to x and y not. Now, what does De Morgan's theorem tell us about this relationship? If we apply De Morgan's theorem here, what are we going to get?
X naught or Y naught.
What's that?
X naught or Y naught.
Yeah, x naught or y naught. This relationship right here is going to be very, very important. All right. So I've got NOR gates. Again, you can probably guess what it is. It's a not or. So same deal. If I have an OR gate with a little inverting bubble on the edge there, I'm going to have this. That f is equal to A or B or C, whatever I do. Wrong news. So I either change and apply x or y. Not. What happens when we apply De Morgan's theorem here? X naught. Good. X naught and y naught. Okay. Any questions about that? Like, these are the relationships that are vital. Okay. So now how do we go about doing the conversions? So, actually, let me put it here. To make this happen, to convert a circuit of AND or whatever, to NAND gates and NOR gates, we're going to apply the involution law. Does anyone remember what that one is? It's the one that says x naught is equal to x, right? We take a double inversion, then we get what we started with. Which seems obvious and sort of not even worth pointing out except for in this instance. So let's go ahead and work out an example. So let's say that I've got a function of A, B, C, and D, and it's equal to A or B, C naught, or B naught, C, D. First, let's go ahead and draw the circuit the way it is, in the AND or two-level realization. So that means that we have, let's see, two AND gates. Remember that our inverses are given to us. So we can say the input is B and C naught. We have another AND gate, B naught, C, and D, and they feed into an OR gate. And also A, right? A is a single literal by itself, which means it feeds as an input to the output gate. and that's our result F. So that's what we've done before. That should be pretty
The
straight.
B is not, right?
Excuse me?
The B on the bottom is not, right?
Yeah.
Okay.
So this is a circuit that we would build sort of knowing what we know today, but what we want to do now is make it more efficient, get it ready for production. So we're going to convert it to a NAND gate circuit. And all we have to do for that is just take F and invert it again, right? Because this is equal to F, right? This relationship holds. So what happens there? We have two things that happen, right? A, our original expression, A or B and C prime, or B prime and C or and D, that gets inverted, and then we invert again. Now when we apply De Morgan's theorem here, just to this first quantity, we're going to get what? A prime and B and C prime and B prime C D prime, and then all of that is still inverted. Does anyone have any questions about how we got from here to here? All right, and then we're done. That's our NAND gates, right? Because we have an AND operation inverted, an AND operation inverted. Everything is ANDed together, and that's inverted. So what that means here is if we draw this guy, well, now we have a NAND gate with B and C naught, and a NAND gate with B naught, C, and D, and then another NAND gate with A prime, and it's still equal to F. There we go. Also, we shaved about half the cost of building this ring. All right. Any questions about this? So, what things happened? There's not a whole lot that happened between what we started with and what we got.
Just a few minor changes.
What's that?
So there's a few minor changes.
Yeah, what changes?
The call it. Well, first the A is not now.
Yeah, that's a good catch. Okay, so let's just write this down. We'll call this procedure for taking an AND OR and converting it to a NAND. So let's see. The first thing that happened was we have to start with, to get a NAND circuit, we have to start with an AND OR, right? Otherwise it won't work. And we'll see why when we do the other example. But we'll say that this is not even really part one, it's like part 0, part -1 says that you first find the minimum sum of products and draw the AND OR logic circuit. That's important. If we don't start with sum of products and we don't start with AND OR, then nothing can happen. Step 2 is literally just change every gate to NAND gates. Replace every gate with a NAND gate. So we took our two AND gates, NOR gates, and replaced them all with AND gates. Step 3, the last step, you noticed, was that we had to change A to A prime. So what that rule states is any single literals that are inputs to the output gate should be inverted. Any single literals, by that we mean just a variable by itself, that is an input to the output gate, right? So any single literal that's an input to the very last gate before the output, that should be inverted. So A became A prime on the input of the output gate, but everything else stayed the same, right? B and C prime stayed, B and C prime, B prime and C and D stayed, B prime and C and D. So to get a NAND and NAND circuit, you gotta start with a sum of products, and draw the AND OR circuit, replace all the gates straight up with NAND gates, and any single literals that are inputs to the output gate should be inverted. And that is all there is to it. Any questions about that? Cool, all right. So from there, let's do the other one. Let's do NOR, NOR. And all we have to do to change it to NOR, NOR is replace, let's see, sum of products up here needs to be product of sums. I guess we're confusing anybody. And it needs to be product of sums so that we can get an OR AND logic circuit, and then we replace every gate with a NOR gate. And other than that, everything stays the same. So this is the procedure we're taking. NOR AND.
This is basically the opposite.
It's exactly the opposite. Yeah.
Write that down, write all that down.
So, if we had a circuit now that is a product of sums, an expression, excuse me, a Boolean expression is the product of sums, say A or B or C and A or B prime or C or A, whoa, a minute, switch gears there for a second, A or C prime or D and B. Well, then to start with, we have 1, 2, 3, 3 OR gates to start with. With A or B or C. Then A or B prime or C, or A or C prime, or D, and all of that ANDed with B. In that case, it is RF. Now we can draw the logic circuit without even doing the Boolean algebra, right? What do we have to do? Make sure, first off, make sure we have an an or and circuit, which we do, because we had a product, or excuse me, a product of sums expression. We're now going to replace every gate with NOR gates. So NOR gate for A, B, and C. NOR gate for A, B prime, C. NOR gate for A, C prime, D. And then finally, a NOR gate which takes all three of these, and B becomes B prime. Cool. Just to say we did, if we took this whole expression, inverted it and inverted it, we would do what? Since these are all ANDed together, it would be OR and inverted, so we would have A or B or C prime, or A or B prime, or C prime, or A or C prime or D prime, or B prime, and then whole thing prime. All right. So that's how we create a circuit of NOR gates. Difference here is we're going to start with product of sum so that we can get or and, then everything else is the same. Any questions about that?
No. Did. And oh.
Okay, so the last thing I'm going to do today, so this was to create two level circuits, right? Or or becomes NAND or NAND NOR. Right, but our circuits are not always that way, right? We saw last time that there can be multiple levels to our circuits. And so what we need is a procedure for converting multi-level circuits to still be circuits of NAND and NOR. It turns out the procedure is basically
This one.
exactly the same. It just needs some tweaks. Okay. So we'll call this multi-level NAND gates and NOR gates. Alright, what I'm going to do is I'm just going to cut this in half. We'll write it down for NAND gates, and we'll write it down for NOR gates. Just to point out the differences. But again, the differences are going to be pretty superficial, just like they were for the two-level circuits. So step one for NAND gate circuits is design a multi-level circuit with an OR gate at the output, right? basically it says you still got to do the thing where it's and or, but it can be broken back as long as the last gate is an OR gate. On the NOR side, it'll be exactly the same. Design a multi-level circuit. With an AND gate at the output. Alright. So for NOR gates, we've got to start with an AND gate at the output. For NAND gates, we've got to start with an OR gate at the output. Step 2, replace all gates with NAND gates. And you can guess over here on the NOR side, step 2 is replace all gates. With NOR gates. So, second step, replace all your gates with whatever gates you're looking for. I'll go ahead and write step 3 for both of them, since it's exactly the same. There is no difference. So, any single literals which are inputs to odd numbered levels should be inverted. Any single literals which are inputs to odd numbered levels should be inverted. I think it was in this class somebody asked, do you have to count the levels from one direction to the other? And I said yes, and it's going to matter. This is why it matters, because this one has to be level 1, so they can be odd numbered, so they can get its literals inverted. And then we would invert level 3 and level 5 and level 7 if we had those going all the way back. But the first one has to be 1, so that it can start off this chain. What's that?
So it's even, you leave it alone.
What's that?
So it's like an even number.
Exactly. It's even, you just leave it alone. So, and that rule holds here for our 2-level examples, right? This is level 1. We inverted that literal. And this was level 2, is an even number level. We left them all alone, right? So you can almost like forget those rules that we do with 2 levels. This governs all of them, right? Even 2-level circuits. All right, let's do an example. Let's say we take this guy. I'll say F, and it's equal to A prime and quantity B prime or C and over parentheses D or D prime, close parentheses, or F and G prime, close brackets, braces, or H and I prime and J prime. That's kind of a ridiculous example. Or K.
H, I, and J.
H, I, and K. So the first thing let's do is let's go ahead and draw let's draw a tree diagram. And I guess we gotta ask ourselves, like, well, where does it start, right? going to start right here. Because there's one big rule, right? We talked about it. We said we might break it from time to time, but there's one major rule that says you've got to, all the levels have to consist of the same gates, right? So that means when you're thinking about the levels, what gave me pause, right, is like, well, we had D or E prime, because that's dependent on C, and that feeds into this next one, which feeds into all these guys, but we could have done this one, this AND gate level first, right? And then we actually could do that, but that is going to drastically change the outcome, right? Because if we start here, this OR operation first, in the first level, or not level 1, but like the input level, right? That's going to radically change it's going to change what the output gate has to be, right? And if we start here on the AND gate, that means, well, we're going to change whatever the output gate is going to be here. So while it doesn't necessarily matter on the surface, it might matter if you're asked to find a specific type of circuit. It might matter which one you start with. If you start with an AND level or start with an OR gate level. We're going to go ahead and start with an OR gate level just because. So that's level 2. Next we can do some ANDs. So let's do that one and that one, which is also 2. Now we can go ahead and do this one. Cool. Next, let's just keep track, right? That was OR, that was AND, and 3. So next up we're going to do OR. Oop, we missed one. We could have done another AND.
Can we do the FG prime?
Yeah, we did FG prime. Also that's 2. Let's see. Now we can do the OR. And that's going to be these guys. What's going to be? Yeah. That guy, and that guy. Just 3. Next we got to do an AND. It's going to be this guy and that guy for 2. Now, could I have done this AND operation down in this level?
Oh, yeah.
Yeah, totally. Right. And then finally, we're going to OR everything, right? So this whole quantity, OR with that quantity, OR with that quantity means we're going to have that 4. Okay.
Nasty.
What's that?
Mine was all nasty.
What's up?
What was the FG ORed as well? The FG prime?
Right here?
Yeah.
What was your question?
Why did you OR with the last one? Because wasn't already ORed with...
I ordered it here.
Yes.
Oh, you're right, yeah. Good catch. There we go, 3. Probably because my sort of brain saw that it was like or FG or HIJ and sort of went with it. But that's what you guys are for. Okay, so let's see. Let's go and count. I'm serious, man. You gotta get up here and do this live. You make lots of mistakes. Count on people to catch it for you. And any professor that gets mad at you for calling them out on their mistakes on the board is a loser.
I remember that. I remember that.
Remember that. Remember I said that. They get mad at you for calling them out for a mistake. You can tell them Derek Johnson said they were losing.
All right.
That's gonna come back to give me in a couple years, right?
I'm trying to beat you up.
So that's C for later. All right. Yeah. Okay. So let's go ahead and count. Yeah, that's a whole soapbox I can do on, but we're gonna focus on this now. So let's see. How many levels do we have? We have 1, and then level 2, then a level 3, level 4, level 5. You know, I asked earlier, would it have mattered if we had done this AND operation here or here? And it really wouldn't have mattered either, right? Because in both cases, they were even levels, right? So it wouldn't even have caused the inputs to be inverted. So who knows? Maybe when you're like laying out the circuit, there might be a reason to scoot him down to level 2 to make room for something else. But all right. So let's see. What do we care about? Number of gates. Just to sort of do our accounting. How many gates?
3,
7. All right. 1, 2, 3, 4, 5,
Oh,
6,
what's that
7.
on the numbers?
Yeah. Next up is number of gate inputs.
Oh. Yeah.
How many we got now?
17.
17. Good. 17. And finally, number of levels, or gate levels,
Ooh, what is this? 5.
is 5.
Ooh, yeah.
Good stuff. All right. So that's how we kind of broke down our analysis here. Doesn't necessarily have a ton to do with converting into NAND gates and NOR gates, but it is a good exercise. All right. Can I already solve this procedure? You got this written down? All right. All right, let's go ahead and draw the circuit here. So now we've kind of got a framework. We can start with, back to back here, we got level 5. And then OR gate, which had what? C or, D or E prime. Then we had a level that consisted of 3 AND gates. And that one took what? So the first one was the output of our OR gate, and C. The second one was F and G prime. And the third one was our HI prime J. All right, those are AND gates. Next up, we had a level of OR gates. It only had one OR gate in it. And that had what? 2 of our AND gates, specifically these 2. And what? B prime. Yeah. Next up, we had another level of AND gates. Maybe we should have moved HIJ down here just to give this AND gate a friend, right? Let's see. That had what the output of our OR gates. Notice that there's a chain, right? Remember our original definition was a level was the maximum number of gates connected in series, right? Every level is going to connect with its previous level at some place, right? Even if you have gates that aren't connected, every level is going to have some sort of link in the chain, right? They're all going to be connected together. Otherwise, they just wouldn't matter. So let's see. Ooh, in fact, never mind. It's a different thing. Okay. What else do we have? We had that, and then we had what? A prime. I was just thinking that was an argument to put HI prime J down here, right? So if it doesn't have a link in the, if it's not part of the chain, right, it should just go until, it shouldn't appear until it's first place. But that's purely just a stylistic thing that I just thought of. That's how I'm gonna do it from now on. Okay. Let's see, A prime, and then finally we have what? Our OR gate. Which again had our AND gate. Our other AND gate, and K, right?
Ooh, yeah.
Boom. And there's F. right, level 1, level 2, level 3, level 4, level 5. Okay, so now that we've come to this place, which of our two more efficient gates, also I'm going to erase this stuff. Are we good? Okay. Which of our more efficient gates can we transform this into? To get a NAND gate circuit, you have to start with an OR gate on the output. To get a NOR gate circuit, you got to stop with an AND gate on the output. So what are we going to have?
NAND.
We're going to have a NAND gate circuit because we have an OR gate on the output. All right, so the first thing we're going to do is we're going to convert everything to NAND gates, right? So we have NAND, and then we have free NANDs. NAND gate, right? That first NAND gate connects to that one. Then we have an AND gate, everybody said OR gate. Then we have, that connects. We have another NAND gate. And then we finish off with a final AND gate. Yeah, that should go there. That should go there. And then output F. That was kind of hard to do without drawing the inputs. Okay, so there we've done our switch over to just NAND gates, right? My bad. All right. So now we go and add the inputs, right? So we'll start here. So D and E prime are in level 5, which means what's going to happen to them?
Inverted.
They're going to get inverted, right? That's going to become D prime and E. Here we're at level 4, which means what's for our inputs?
They say the
Means
same.
they're all going to stay the same, right? They're in an even numbered level, so they're all the same. That's going to be C, that's going to be F, that's going to be G prime, that's going to be A, it's getting tired of me. That's going to be I prime, that's going to be J. All right, next up we've got here, this is level 3, which means B prime is going to become just B, all right? Then we're at level 2, which is even, so A prime will remain the same. And then finally, the last one, level 1 here, has an input K, which is going to become K prime.
Can you post the answer on number 3?
What's that?
Post the answer on number 3.
Can I post the answer to number 3? I guess so, yeah. It's not like super relevant to this, but you'd have to like triage those questions, right?
Hmm?
What? Never mind. I'll tease you. Don't worry about it. Okay. Any questions about this?
When you're recording the lecture.
We just talked about it. You're supposed to like.
Class is over.
Class isn't over. Is it over?
It's
What time is it?
11:51.
Oh, guys, class is over. What do you have to do?
You want to learn?
Yeah, that's my man. You see, we don't care. It's the coolest stuff ever. All right. NAND gates and NAND gates. All right. So there we go. There is the procedure, right? You start with a multi-level circuit of AND gates and OR gates. Remember that every level has to have the same type of gates. You have some flexibility, right? This one could have been level 2 instead of level 4. If you have OR gate on the output, then you're going to get NAND gates. If you have an AND gate on the output, you're going to get NOR gates. You flip them all the odd number levels get inverted. Yes, I will post the solutions to assignment number 3. Yes, the lecture is being spoiled. Are there any other questions? All right, man. I'll see you guys on Wednesday.
Thank you.
What's up?
Yeah, one question for you.
Yeah.
So when you were doing the what's it called, the feed diagram, the really question before, you
Yeah.
had that long list.
Yeah.
Stuff like this. You have no money, or you just have to do that?
Yeah, you start from the innermost one, and remember there was some flexibility about what we could do. But the problem is, like, you have to start with things that don't depend on other things, right?
Okay.
So everything else, like for example, there was what? Like D and E prime, so D or E prime,
Yeah.
and now it's ANDed with C, right? Well, which means that the output of D or E prime was going to be the input to that AND gate with C, right? Which means that you had to do that OR operation first.
Okay.
Does that make sense? Yeah.
So that's like, so you have a OR gate, that's how you do that, the D&E.
Yeah.
And then that gets handed to a gate with C, and then.
Yeah.
That's
So you just got to make sure. So as long as if your operation is free to do at that moment, right? You can do it then on the tree. Just don't forget you can't put different types of operations. You can't put an AND gate and OR gate on the same level.
And what is the B right here? Go into this one right here?
Because see, look, it's B or all of that, or
Oh,
all of
okay.
that, right? Yeah.
That makes sense. Cool.
Yeah.
Thank you.
You're welcome.